about XNORNet. And here is our contents, including the overview of the project, the background, the design, and the testing and deliverables, and schedule and team members. Okay, here are the overview of our project. The idea of our project was based on the paper, which is the same with one of last group, XNORNet image-net classification. The paper illustrated the principle of XNORNet and implemented an XNORNet to significantly reduce the consumption in memory and computation. Then we expand the idea with some why not we try some existing neural network to implement this, like TensorFlow. TensorFlow is an open source software library for neural network, and it is easy to use, and you will find the GPU version of TensorFlow is much faster than the CPU part. However, the GPU part is not so easy to use because first you need to have a high-end graphic card, and then you need to install the right version of the driver and the corresponding version of CUDA and the CUDA, which is a necessary requirement, is always changing as Google releases a new build of the TensorFlow. So in some cases, I see some people still use the CPU version of TensorFlow. That is one of the reasons that we want to improve the performance of TensorFlow with XNORNet. Here, the background of our project. Neural network requires a lot of computation, and most of them are floating point operations, which is the strength of GPU. However, if we binarize the input and the parameters of the neural network to make it a binary convolutional neural network, much computation could be saved. Compared to the non-binarized network, a large number of math operations have become bit operations. This saves a lot of space and time for forward propagation, and this makes the application threshold of neural network much lower. Here is the design of our project. The base of the project is binarization. Basically, there are two ways of binarization. The first way is very intuitive. Just use the sign function to make all positive number, including 0, positive 1, and make all negative number negative 1. The second one seems a little more complicated than the first one, because we use a probability function to calculate the probability of each number to be positive 1 or negative 1. It solves the problem of the first way, that there is no difference in all positive or negative numbers. Although the second way seems more reasonable, it brings another problem that it takes a lot of time to generate a random number and to calculate, which conflicts our intention for reducing computation time. Therefore, we will still use the first one in our project, but we will also try the second way as a comparison to see how much more time it would take, and how much more accuracy it would bring, and to find a balance. Then the neural network would be simplified to a binarized neural network, and there is a different block in XNORNet. On the left side is a typical block in the convolutional neural network. First convolutional, and at last the pooling layer. The pooling layer applies any type of pooling of the input and pooling them. Apply pooling layer at the after convolutional layer results in significant loss of information. For example, max pooling on binary input returns a tensor that most of its elements would be positive 1. Therefore, we will put the pooling layer after the convolution and here's a structure of the block on the right side. Frankly speaking, so far this theory we only learned from the paper, and we haven't tried this part, and so we don't know how much it would affect the result until we really try it.
What do you mean by affect the result? Try what?
Try to put in the consequence of the different layers and how much it would affect in a binary network.
They tested this, the right part in the paper, right?
Tested in the paper, but I haven't tried it.
Okay.
And here's the testing and deliverables. Our testing data including the first ImageNet data and some other images. ImageNet is an image database organized according to the website called WordNet, and each node of it has hundreds of thousands of images. Also, I have some other images from Professor Crandall in my independent study. I don't know if the images from ImageNet are too many for our experiments, so maybe we can try some images with less categories like this. I have two data sets of diseased cells. The first one has 3 categories and the second one has 8. So far, I ran it on TensorFlow and I have an accuracy of 95%. I run it for 100 epochs, and each epoch takes about 1 minute with a training set of 30,000 images. We will see how much time it will save in our project and how much accuracy it would lose. The deliverables will include the TensorFlow-based external net and the test result of the testing data mentioned above. Here's the schedule of our project, and here's our team members. I will be in charge of the setup of the external net on TensorFlow, and Zhengyi will be in charge of to try some comparison part parallelly, and then we will try to comparison my part and his part to find a balance.
Back to the deliverable slide. So basically, your project has nothing to do with the hardware, with digital logic, with gates, right?
Yeah, at first we tried to implement an FPGA, but last time when I proposed it, you said you don't need to replace an FPGA, so
No, you don't have to do it on FPGA, but you have to work on some hardware stuff. Otherwise, you can easily download this XML code from GitHub with the testing data of ImageNet. I even have the training data, the trained data, the trained network. So even we don't need to discuss about hardware or software in this slide. The only thing is new is the medical image you used. So basically, you only need to train a new XNOR net with new data inputs. That's all. That's all, right? You just use the new inputs to train the neural network. That's all. I don't think this is good enough.
So you mean we need to do that on which there?
First, you can follow the previous group, do some digital logic design.
Okay.
You don't have to synthesize them on FPGA, but you need to do some simulation at gate level. This is one option. The second option is that you can continue to work on this software-based project. I'm also fine with that, but you have to guarantee that the accuracy has to reach some level. Otherwise, if you use new data input like the medical images, I can guarantee that the accuracy will be very low. For example, let's say 10% accuracy.
Could you explain more about the reason for that?
Because the XNOR net is a very simplified topology. You cannot, I believe that medical image is more complicated than that in the image net.
Should I show some examples of the images that are each one from the three categories in the dataset one?
For me, the data size is very small. And in ImageNet, there are 1,000 categories. But here, only 3 or 8. If you can guarantee 99% accuracy, try to optimize the network to 99% accuracy.
So far, I've tried on TensorFlow without any binary network. Accuracy could only reach 95%.
95%, okay.
Actually, I think the binary network or XNOR network should lower the accuracy.
Yes.
Much better.
What topology did you use? What network did you use?
Oh, I tried that with TensorFlow. I built a 4-layer neural network.
Fully connected,
yeah.
4-layer neural network. Why did you try only 4-layer?
Because I'm kind of new, so I just built first I built a simple network, and then I will improve it to try to improve it. So far, the 4-layer network it took a lot of time running on my GPU, and I will try to improve it in the future. That is the content of another image study.
Again, you have two options. The first one is follow the previous work, do some hardware design. The second one is that you guarantee you can optimize it at least 98% accuracy.
Okay,
Use some advanced topology like AlexNet, RaceNet 50. Do not mention about overhead, computing overhead. This is not an excuse, right? You have GPUs, you can train those. This is a very small data set. And I think you can do it. You can make it. For those full precision CNN, maybe 98%. For XNOR net, maybe 95%. If you are confident in doing this, you can continue to work on the software part. Otherwise, you have to use the hardware design. Follow the previous rule.
Okay, I don't think I can guarantee the 95%, so I would choose the hardware part.
You don't even try, right? You don't even try. AlexNet.
I'm afraid of if I cannot reach that, you will fail us.
What's the size of the image?
Oh, the dataset one is about.
No, not data size, The size of one image.
Oh.
For ImageNet, it's 224 times 200. The same.
Also, yeah.
Okay. I still do not understand why you directly try AlexNet, because this is the shallowest CNN created by previous work.
I'd like to try, and I will try my best, but I just cannot guarantee some specific rate of accuracy.
Otherwise, if you only get maybe 60% accuracy, it's meaningless, right?
Yeah, 6% I think that is too low, but
No. By XNOR net, it's very easy for you to get such accuracy.
I think I can try my best to try our best to get at least 55 or 90, but I just cannot guarantee.
My point is that you have to propose something to improve the accuracy. Otherwise, you just use the new data set to train an existing network. You don't even have to change anything. You just write a script and do the training thing. That's all. and then you get the accuracy, right? Whether it's good or not, you will report that accuracy. Basically, you did nothing.
Actually, we have to implement ExponNet with TensorFlow.
No, I don't think you can do that. You can easily download the source code from the internet.
Okay, so I think we will try the hardware part. So there's no other codes for reference.
For hardware, there's no code, existing code.
Yeah, so I think we will try some part on which there are some of the Git level.
Okay.